Hi everyone, in this video we're going to look at Ka and pKa and how that can be used to determine an acid's strength as well as a base strength. Okay, so I have a generic example of an acid-base reaction up above. Ha is just any acid with water producing A- and H3O+. So if we were going to write an equilibrium expression for this, we would call it a Ka. This is because this is an acid dissociation constant. It would tell me something about the ability for this acid to dissociate into A- and hydronium ion. And this is equal to, as any equilibrium expression is, the products, the concentrations of the products, so A- multiplied by the concentration of H3O+, divided by the concentration of the reactants. So Ha, and then water is typically omitted from the equilibrium expression because it is a constant. It's a pure liquid. Okay, the molarity of water in water is not going to change significantly, so we can ignore it from the equilibrium expression. So Ka ranges from 10 to the negative 60th at one end, all the way up through 10 to the 10th, roughly. Okay, so that's quite a range. Ka is written as an exponent, and so that's what makes Ka a little bit less nice to work with, is because often the numbers are either very, very large or very, very small. Okay, so if we change Ka to pKa, that's more often what we'll use in this course. Okay, so pKa is equal to negative log of the Ka. So this takes Ka, that exponential number, and translates it into a number that's between negative 10 and about 60. Okay, so negative 10 to 60 is a lot smaller, a lot more reasonable to work with than 10 to the minus 60th all the way through 10 to the 10th. Let's look at a few examples. HCl is one that we've seen a couple times already. So the Ka is about 10 to the 7th. That's a really large Ka. So when we think about what that means, is large Ka means it's a heavily product-favored reaction. Take a look at the fraction here. If we have a number that's larger than 1, that means my numerator has to be larger than the denominator. Okay? And if it's really huge, then this is very large compared to the denominator. So we have a lot more products than reactants. Just able to know that by thinking about the math here. So if we take 10 to the 7th and plug it into my pKa equation, we have log base 10, so that's going to take this 10 to the 7th and make it 7, and then we have the negative sign, so pKa is negative 7. Sulfuric acid is another common acid you probably came across. It has a Ka of 10 to the 5th. So again, a very large Ka would indicate a product-favored reaction with a pKa of negative 5. Let's go a little bit higher now. Let's look at acetic acid, CH3COOH. This has a Ka about 10 to the negative 4.7. So we've crossed a threshold now. We are less than 1. 10 to the negative number is going to be a number less than 1. So that means my denominator now is larger than the numerator, and we have a reactant-favored process. So this would be a positive 4.7. Another example, water, 10 to the negative 15.7, which would translate to a pKa of 15.7. And even more with methane, 10 to the negative 60th, with a pKa of 60. Okay, so with this little bit of data, and you'll have a complete sheet at your disposal to practice with, we can look and make a couple connections here. Okay, so as my Ka gets smaller, my acids are getting weaker. Okay, so we have product favored with very large Kas, indicating complete dissociation for the strong acids. And then as we get weaker, we get much less dissociation, a much more reactant-favored process there. So as the Ka gets smaller, weaker acid, stronger acid as it gets larger. Now, that's the opposite for pKa, right? A negative pKa, a very small pKa, indicates a strong acid, and as we get larger and larger, we get weaker and weaker, okay? So since we will be using pKa for the most part in this course, we want to make sure we understand that a low pKa or a negative pKa is going to mean a strong acid, and a very large pKa is going to mean a weak acid, okay? So then when we think about how does this connect up to our bases and strength, okay? So we can see very straightforward, okay, the number is what it is corresponding to there. Okay, so what does that tell me about the conjugate base, right? Well, the conjugate base of HCl is Cl minus. Conjugate base of H2SO4 is HSO4 minus. The conjugate base of acetic acid is CH3COO minus. The conjugate base of water is HO minus. Conjugate base of methane is CH3 minus. Okay? So, if HCl is a strong acid, what does that say about Cl minus? If we put Cl minus, is it going to be able to take a proton from something? Probably not really. If HCl wants to give it off so quickly, Cl minus isn't going to want to take it back very readily. So it turns that the conjugate bases would then be weak for very strong acids. Okay? And as we go down, the weaker the base, the stronger the conjugate. The weaker the acid, the stronger the conjugate base is. Okay? The weaker the acid, the stronger the conjugate base is. So the strongest base that we could really ever see is going to be a carbanion, a charged carbon nucleophile. Okay? So, strong acids make weak bases. Weak acids make strong bases. Just want to say it again to reiterate that fact, okay? Of course we have our strong acids and our weak acids, but I want to break this down a little bit more for us and add some discrete lines that we can work with. So, for our strong acids, we have pKa's less than 0. So anything with a negative pKa we're going to classify as a strong acid. These are things like HCl, HBr, HI, sulfuric, nitric. Okay, these are common strong acids that you already know. All right. Then weak acids, we are going to say are having pKa's between 0 and 11. So some of the common ones that you'll see will be acetic acid, like we have here on our condensed chart. HF is one of the halogenated acids that is not a strong acid. Okay, so keep in mind that that's weak. Phosphoric acid is a weak acid. Ammonium, NH4+, is considered to be a weak acid with a pKa around 9 or 10 or so. And then phenols, another common class of organic acids, around pKa 11 or so. And then the final category will be what I call very weak acids. And these will function as an acid in a few cases, but these will have pKa's greater than 11. So some common ones, things like hydroxide, things like water, having a conjugate base of hydroxide. The pKa of water is 15.7. Other alcohols, in terms of functional groups, alkanes, alkenes, and alkynes all have pKa's greater than 11, okay? So those are some common very weak acids that we will encounter. So I want you to keep these cutoffs in mind because we will use them, especially later on this semester when we start thinking about what's going to favor substitution reactions versus elimination reactions. This is going to be our guide, okay? It can help us to predict reaction outcomes. So if you have questions, reach out to me, and thank you for watching.